Hello, dear learners. I heartily welcome you all in the fifth lecture of this series on renewable energy sources. In the fourth lecture, we understood in depth of solar energy, availability of solar radiation, solar constant, and seasonal variation of solar energy on the earth. We understood all about the solar energy, but practically, how can we measure solar radiation? I again repeat that one. Practically, how can we measure solar radiation? It is possible to measure solar radiation. Today, in this lecture, we will study in detail how to measure solar radiation. That is an instrument available to measure solar radiation. As we know that solar radiation emits from the sun, it has to travel a long distance to come on the Earth's surface. As we are already studied in the availability of solar radiation on the Earth, we will consider solar radiation in terms of solar flux. Actually, the solar flux density is reduced by about 30% compared to extraterrestrial radiation flux on a sunny day, and is reduced by as much as 90% on a cloudy day. Why it is so? And large difference in extraterrestrial and Earth surface radiation flux density? The answer to this question is quite simple. In extraterrestrial, there is no absorptive particles, vapors, or other things. So the flux density is 100%. Whenever solar radiation comes in the Earth atmosphere, it gets absorbed, scattered, reflected, or transmitted, as atmosphere consists of cloud, dust particles, molecules, etc. All these processes result in reduction of the energy flux density. As a result of above mentioned process, the direct radiation reaching the Earth's surface never exceed 80% of the original extraterrestrial energy flux, or more appropriately 70%. As we know that short wave radiations are the radiation in the wavelength range from 0.15 to 0.4 micrometer, comes directly from the sun. It includes both beam and diffuse components. Long wave radiations are the radiations which with wavelength 0.7 micrometer or longer originates from the sources at near ambient temperatures, atmosphere, Earth surface, light collectors, and other bodies. Again, the long wave radiations are the radiations with wavelength 0.7 micrometer or longer. The solar radiation reaching the Earth is highly variable and depends on the state of the atmosphere at a specific place. Two atmospheric processes can significantly affect the incident radiation, that are scattering and absorption. Scattering is caused by interaction of the radiation with molecules, water, and dust particle in the air. How much light is scattered depends on the number of particles in the atmosphere. Wavelength of radiation, particle size, and the total air mass the radiation comes through. While absorption occurs upon interaction of the radiation with certain molecules such as ozone that absorb short wave radiation that are ultraviolet, water vapors and carbon dioxide. Again we know that carbon dioxide absorbs longer wave radiations. Due to these processes, out of the whole spectrum of solar radiation, only a small portion reaches the Earth's surface. As a result, the main wavelength range to be considered for solar application is up to 4 micrometer. This 4 micrometer number is calculated in the previous lecture by Wien's law. The amount of solar radiation on the Earth's surface can be instrumentally measured, and precise measurement of solar data are important for providing background for solar energy conversion applications. Generally, instrument which measure radiant energy is called radiometer. There are two important types of instrument to measure solar radiation: pyranometer, an instrument which measures total short wave radiations on a horizontal plane surface from hemispherical sky, and second one is periheliometer, an instrument which measures direct solar beam on a plane surface at normal incidence. There are different types of periheliometers. According to Duff and Beckman, Abbott silver disc periheliometer and Armstrong compensation periheliometer are important primary standard instrument. Epilenormal incident periheliometer is a common instrument used for practical measurements in the US, that is United States. Kip and Zonen actinometer is widely used in Europe. Kip and Zonen are the names of the instrument that are the actinometer which is widely used in Europe, while epilenormal incident periheliometer is commonly used in United States. Both of these instruments are calibrated against the primary standard methods. And what are the primary standard instruments? That is the Abbott silver disc periheliometer and Armstrong compensation periheliometer. Here we will describe a basic instrument used to measure the solar radiation is Armstrong periheliometer. The amount of solar radiation absorbed by a known area in a fixed time can be found out by this an instrument known as Armstrong periheliometer. Armstrong periheliometer consists of two black plates, S1 and S2. The plate S1 is exposed to solar radiations and plate S2 is shielded by a cover so that it does not receive any solar radiations. Plate S1 acts as a hot junction and plate S2 is shielded by a cover so that it does not receive solar radiation and acts as a cold junction of thermocouple. Thermocouple has a sensitive millivolt meter in the range of 0 to 10. When both the plates S1 and S2 are shielded from solar radiation, both thermocouple junctions are at same temperature, so millivolt meter shows 0 EMF. Now plate S1 is exposed. Plate S1 is exposed to solar radiation and plate S2 is kept shielded. So plate S1 heat up due to solar radiation. As a result, an EMF is generated which is shown by a millivolt meter. The voltmeter reading can be recorded, and by doing some numerical calculation over a period of time, solar radiation flux can be calculated. In this particular diagram, we have attached a galvanometer here to note the deflection or imbalance in the temperature between the two junctions at S1 and S2. There is a voltmeter which measures the voltage produced due to uneven temperature, or which is called as the thermo EMF. This is a battery. K indicates the key that indicates the milliammeter which used to record the current, and RH is the variable resistance, whereas M is the shield. Now we will concentrate on working of this Armstrong pyriheliometer when both the plates S1 and S2 are at same temperature. Millivolt meter shows 0 EMF. When the plate S1 is exposed to solar radiation and plate S2 is kept shielded by a cover M, an EMF is generated which is shown by a millivolt meter V. A number of readings are recorded at a fixed interval of time. A number of readings are recorded over a fixed interval of time. Let A be the area of plate S1, which is measured in centimeters square by using a ruler. Alpha be the absorption coefficient of plate S1. H be the amount of heat flux which is measured in calories, be incident on the surface of the strip in 1 minute. Therefore, amount of solar radiation absorbed in 1 minute by plate S1 is equals to H into A into alpha. Therefore, heat produced in 1 minute or in 60 seconds in the plate S2 is equal to voltage into current into 60 upon 4.2 from equation 1 and 2. This is equation 1 and equation 2. Whenever a milliammeter shows 0 EMF, it means both the plates are at same temperature. Therefore, equating equation 1 and 2 for the same amount of time for 1 minute, S1 received H into A into alpha amount of solar radiation, while the heat produced in the S2 is equals to V into I into 60 upon 4.2. From equation 1 and 2, H into A into alpha equals to V into I into 60 upon 4.2. Therefore, by some arrangements, we can find out H is equals to V into I into 60 upon 4.2 into A into alpha. So, the amount of solar radiation flux can be calculated by measuring voltage which is produced in voltmeter, current which is recorded by milliammeter, 60